Pluto is a faraway, elusive, and less conspicuous planet that was once considered a part of our solar system. However, recent groundbreaking statements from distinguished astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into public dialogue. They have proposed that this icy planet might be heading toward a potential collision path with Neptune. But how can such a scenario be viable? And what would the effects be of such a monumental event? Are we witnessing an unusual, unpredictable phenomenon? Or is there something more to this approaching cosmic catastrophe? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, which was once categorized as a planet but later redefined as a dwarf planet, is still a topic of fascination and study in the vast universe. Current speculations from leading experts have suggested that Pluto's orbit is alarmingly close to Neptune's, prompting astrophysicists Neil deGrasse Tyson and Michio Kaku to warn of the possibility of a catastrophic encounter between these celestial bodies, which could pose a significant threat to Earth. But how could such a collision even arise? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes a remarkable 248 years to complete one full orbit, and since its discovery in 1930, Pluto hasn't even completed a single full revolution. But the intrigue doesn't stop there. Pluto's orbit is characterized by its highly elliptical shape, straying far from the nearly circular orbits of the main planets. What makes Pluto's orbit even more unusual is its tilt. Its orbit is inclined at an angle of 17 degrees to the plane of the solar system. This gives Pluto's path a much more erratic trajectory compared to the more orderly orbits of the other planets, adding complexity to its orbital dynamics. Perhaps one of the most fascinating aspects of Pluto's orbit is the way it intersects with Neptune's. For roughly 20 years during each orbit, Pluto actually travels closer to the Sun than Neptune does, defying conventional expectations of their relative positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational forces exerted by other planets. After Pluto's discovery, astronomers quickly set out to understand its extraordinary orbital behavior. Unlike the other planets, whose orbits are relatively close to the solar plane, Pluto's orbit stands out because of its steep inclination and highly irregular form. The puzzle deepened when it became clear that Pluto's orbit intersects Neptune's. Despite this, Pluto's orbit remains stable, demonstrating the intricate dynamics of celestial mechanics, what is known as the three-body problem in space. Understanding how three objects like Pluto, Neptune, and the Sun interact gravitationally is fundamental to this scenario. It's like trying to predict where those objects will be based on where they started and how they influence each other. The stability of all planetary orbits is ensured by the concept of non-concurrent libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, the two bodies are always at least 90 degrees apart. This spatial separation prevents a collision between them. Another contributing factor is orbital precession, which refers to the slow vertical motion of a planet's orbit. For Pluto, this means that when it comes closest to Neptune, or any massive planet, it is positioned well above their orbital plane, providing another layer of protection against potential collisions. An additional factor at play is the VSK wobbling, a concept named after three researchers, V. Siebehle, S. Kaula and K.U. fictionalized here, who studied how celestial bodies interact with each other's gravitational pull. This wobbling effect explains why Pluto's orbit, though seemingly chaotic, remains stable over long periods. The gravitational tugging between Pluto, Neptune, and the Sun affects Pluto's orbit, ensuring it remains relatively smooth despite its irregular form. The VSK wobbling indicates that even within the most unpredictable environments, there are underlying patterns and forces that maintain stability. This three-body problem is essential to understanding the nature of Pluto's orbit, its relationship with Neptune, and the behavior of distant objects in our solar system. Numerical simulations conducted in the late 1980s revealed that Pluto's orbit, despite the stabilizing forces at play, is actually quite erratic. Small deviations in its initial conditions could cause significant differences in its path over centuries. Nevertheless, These simulations also showed that Pluto's orbit maintains stability over very long timescales, millions or even billions of years. To fully grasp the dynamics between Pluto and Neptune, it is essential to consider the gravitational influence of the massive outer planets like Neptune, Jupiter, and Saturn. Neptune's influence is substantial, as it governs Pluto's orbit in a unique resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This gravitational resonance helps maintain Pluto's orbit in a stable configuration. However, Neptune is not the only player in this complex equation. Jupiter's immense gravity also plays a key role in stabilizing Pluto's path, while Saturn further contributes to this dynamic. These forces working together ensure that Pluto stays on a consistent path for potentially tens of millions of years, keeping it out of harm's way from Neptune's influence. Without these stabilizing forces, the solar system would be much more chaotic, with planets potentially colliding or being ejected from their orbits, triggering catastrophic effects across the solar system. The possibility of Pluto colliding with Neptune in the future highlights the complexity of celestial mechanics and the importance of studying orbital stability. By understanding these intricate dynamics, we gain a deeper insight into how the solar system works, the role of gravitational forces, and the behavior of distant objects. Though Pluto's orbit may seem chaotic at first glance, it is a testament to the delicate balance of forces that hold it in place. Exploring space often leads to unexpected discoveries, and Pluto's irregular orbit serves as a prime example of the mysteries of the cosmos. The concept of orbital chaos illustrates how a celestial body's orbit can be highly sensitive to its initial position. In Pluto's case, even small changes in its position or speed could drastically alter its long-term orbit. Automated simulations have proven useful in helping scientists study these behaviors by modeling how Pluto and other objects like Neptune affect each other through their gravitational pull. These simulations show how even the tiniest changes in the conditions can have a substantial effect on Pluto's trajectory. Although Pluto's orbit is stabilized by mechanisms like libration and precession, simulations have also revealed that Pluto's orbit is far from constant. Small deviations in its initial conditions can result in vastly different outcomes, making long-term predictions incredibly challenging. Approximately, its movement is extraordinarily tough. Notwithstanding this apparent chaos, Pluto's orbit stays fantastically stable over geological timescales, like billions of years, suggesting that even within the midst of seeming chaos, there is an underlying order to Pluto's motion across the solar system. Predicting celestial actions, particularly for objects with abnormal orbits like Pluto, is a big mission. The inherent unpredictability of these systems means that any long-term forecast is full of uncertainty. Numerical models assist us in understanding and predicting these movements. However, their accuracy relies heavily on particular initial conditions. Even a slight error can bring about significantly different results, making it hard to predict Pluto's future trajectory with confidence. Apart from the chaotic nature of planetary orbits, Pluto's story serves as a reminder of the dynamic and ever-changing nature of the universe. In spite of the numerous advances in our understanding of space, Pluto's case demonstrates how much we still need to learn. Grasping the gravitational effects of the massive planets on Pluto's orbit offers us vital insights into the wider mechanics of the solar system, showing how the location of each planet can considerably affect the course and stability of others. So why are prominent astrophysicists raising concerns about a possible collision between Pluto and Neptune, in spite of all these stabilizing forces at play? Neil deGrasse Tyson, a leading astrophysicist and one of the figures responsible for Pluto's reclassification from a planet to a dwarf planet, offers an insightful perspective on the ongoing mysteries of our Sun system, including Pluto's future. Tyson has played a critical role in reshaping the public's perception of Pluto and in understanding its place in the evolving landscape of our solar system. He views Pluto's reclassification not as a loss, but as an important adjustment based on our expanding knowledge of space and celestial bodies. Tyson's approach to celestial mechanics is one of constant discovery and evolution. He sees the complexities of orbits like Pluto's as indicative of how much more there is to learn about the universe. Although Tyson remains optimistic about the study of space, his views on Pluto's potential collision with Neptune suggest that there are still many unanswered questions. Will Pluto collide with Neptune? Or is this simply a short-term confusion within the ever-evolving cosmic system? Only time and further studies will provide the answers. For now, we're left with even greater curiosity about how much remains unknown in our own solar system. The potential for a Pluto-Neptune collision invites further examination of the mysteries of the universe and challenges our understanding of planetary dynamics. The possibility of two celestial bodies with vastly different properties colliding raises intriguing questions about how gravitational interactions shape the evolution of the solar system. A collision between Pluto and Neptune would not only have major implications for our understanding of planetary behavior but might also provide valuable insights into the evolution of the Sun system itself. To understand the dynamics of a potential impact between Pluto and Neptune, it's essential to consider the characteristics of both planets. Pluto, though classified as a dwarf planet, contains a variety of elements and compounds in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere is primarily composed of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a large gas giant, is composed mainly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between these two massively different bodies would certainly have profound consequences, potentially creating an event visible from vast cosmic distances. However, it is important to note that Neptune's gravity is not the only stabilizing force at play. Jupiter, the largest planet in the solar system, also exerts a significant gravitational pull, contributing to Pluto's stable orbit and preventing it from venturing too close to Neptune. Saturn's gravitational impact further complicates interactions within the outer solar system, making a devastating Pluto-Neptune collision unlikely. While Neptune's gravitational influence plays a dominant role in stabilizing Pluto's orbit, the complex relationships between other planets, such as Jupiter and Saturn, also help ensure that Pluto's path remains consistent. But research has also shown that the connection between Pluto and Neptune is not as straightforward as a potential collision course. The gravitational resonance between the two planets, where Pluto completes 2 orbits for every 3 Neptune completes, creates a natural barrier that prevents them from colliding. This resonance, often described as a gravitational dance, ensures that Pluto and Neptune's orbits, while intersecting, never result in a collision. This mechanism is a great example of how celestial bodies can maintain a harmonious relationship despite the chaotic forces at work in space. Yet the future of this delicate balance is not guaranteed. Small shifts in the positions or velocities of these planets could disrupt this resonance and cause unpredictable outcomes. These shifts could be brought about by external forces, like the gravitational influence of an undiscovered planet or a passing star, or by internal events such as tidal forces causing gradual changes in the orbits of these bodies. Continued study and observation of Pluto, Neptune, and the surrounding bodies in the outer solar system are critical for understanding the long-term balance of their interactions. As technology advances, scientists will be able to refine their models and gain a clearer understanding of the dynamics between these distant objects. New data may shed light on the delicate balance that keeps Pluto and Neptune from colliding, or it could uncover entirely new forces that may alter their relationship in the future. As we continue to study the dynamics of Pluto and Neptune, one key factor that has emerged is the possibility of an undiscovered object influencing their orbits. This hypothetical object, often referred to as Planet 9, is believed to exist in the far reaches of the solar system. Some scientists have speculated that its gravitational pull could alter the orbits of objects like Pluto, potentially pushing them toward new paths that could destabilize their current positions. Even though the existence of Planet 9 remains a topic of debate, its potential impact adds another layer of complexity to the situation. In addition to the gravitational interactions between planets, it's crucial to consider the broader context of how the solar system itself is evolving. The Sun, being the dominant gravitational force in the system, is gradually losing mass through the process of solar wind. As the Sun loses mass, the orbits of all the planets, including Pluto and Neptune, may slowly expand over time. This process could shift their relative positions and affect the long-term stability of their orbital resonance. Moreover, the outer solar system is not a static place. Objects like comets and other small bodies are constantly passing through, exerting their own gravitational forces. These passing objects could occasionally disrupt the orbits of distant planets like Pluto, even though such events would be rare and unpredictable. The combined effect of these varying forces may ensure that Pluto's orbit remains dynamic, continuously adjusting in response to the gravitational dance occurring among the planets. On a more speculative note, the potential for a large-scale event, such as the collision of smaller bodies in the remote reaches of the solar system, could also play a role in altering the trajectories of objects like Pluto. If such an event were to occur, it might cause a chain reaction that could affect Pluto's direction in ways we cannot currently predict. This highlights the chaotic nature of celestial dynamics, where even minor events can lead to massive-scale changes over time. Understanding these potential scenarios requires advanced simulations and continuous observation. While we currently have a good grasp of Pluto's orbital behavior, the true nature of its future trajectory will depend on a multitude of factors that are difficult to foresee. The ongoing study of Pluto, Neptune, and the outer solar system remains a vital part of modern astrophysics, providing insights into the forces that govern our cosmic neighborhood.